For almost 4.6 billion years, our solar system has been a pocket of relative order in the vast quiet emptiness of space. It's a family of planets, each one unique, all dancing to the rhythm of a single star. But it wasn't always this way. Before the planets, even before the sun, there was just a cold, dark, and mind-bogglingly huge cloud of gas and dust. So, what flipped the switch? What cosmic event kicked off the creation of our world? Let's take a journey back in time to witness the chaotic, violent, and absolutely magnificent birth of our solar system. Our story starts in a place that you'd barely recognize. Floating in a quiet arm of the Milky Way was a colossal cloud of interstellar gas and dust, what scientists call a giant molecular cloud. This was our solar nebula. It was immense, cold, and dark, mostly made of hydrogen and helium left over from the Big Bang. But it was also sprinkled with heavier elements, carbon, oxygen, iron, you name it, all forged in the hearts of long-dead stars and scattered across the galaxy. This was literal stardust, the raw material for everything to come. For a while, this cloud just drifted in a delicate balance. The inward pull of its own gravity was perfectly matched by the outward push of its gas pressure. But that peace wasn't meant to last. Our solar system was likely born from violence. The leading theory is that a cataclysmic event gave our nebula the nudge it needed. The explosion of a nearby massive star, a supernova. We find evidence for this cosmic trigger today inside ancient meteorites, which hold the decay products of elements that could only have been created in that kind of fiery explosion. The shockwave from that supernova tore through space, slamming into our calm cloud of gas and dust. That powerful squeeze was all it took. The fragile balance was broken, and gravity started to win. The cloud began to collapse in on itself, and in that moment, the birth of our solar system began. As the cloud collapsed, a fundamental law of physics took over, the conservation of angular momentum. Think of a figure skater pulling in their arms to spin faster. As all that gas and dust got pulled inward, the whole cloud started to rotate faster and faster. Over about 100,000 years, this rapid spin caused the cloud to flatten out, transforming the once puffy nebula into a vast, rotating plate-like structure, a protoplanetary disk. At the very heart of this spinning disk, things got incredibly dense. Gravity just kept pulling more and more gas and dust into the center. The pressure and temperature skyrocketed, and a protostar, our infant sun, began to glow. This baby sun was greedy, gobbling up about 99.9% of all the mass from the original cloud. That remaining sliver of material, just 0.1% of the total, formed the sprawling disk that stretched for billions of kilometers. It might not sound like much, but in that thin, spinning platter of stardust and gas was everything needed to build all the planets, moons, and asteroids we know. The stage was set. The cosmic construction was about to begin. Within this protoplanetary disk, a crucial dividing line appeared, all thanks to the heat blasting from the young proto-sun at its center. This created two completely different neighborhoods for planet formation. Close to the protostar, the heat was blistering. It was so hot that only materials with high boiling points, like metals and rocky silicate minerals, could condense into solids. All the lighter stuff, water, methane, and ammonia, stayed as gas and got pushed outward. This hot inner zone was where the rocky terrestrial planets would be born. Mercury, Venus, Earth, and Mars. They were built from the heavy stuff that could take the heat. Further out in the disk, beyond a boundary known as the frost line, it was much, much colder. Here, it was cool enough for not just rock and metal to solidify, but for huge amounts of water, ammonia, and methane to freeze into solid ice particles. This meant there was way more solid material to build with. This cold, ice-rich outer region was the domain of the giants. It's where Jupiter, Saturn, Uranus, and Neptune would form, with access to a massive buffet of building blocks. This simple division explains the basic layout of our solar system. Small, dense, rocky worlds on the inside, and massive gas and ice giants on the outside. With the materials sorted, the real work of building planets began. This process is called accretion, and it started small. Microscopic dust grains started sticking together through gentle bumps and static electricity, kind of like how dust bunnies form under your bed. Over millions of years, these clumps grew from grains to pebbles, and from pebbles to boulders. Once they got big enough, their own gravity started pulling in more material. These growing bodies, now kilometers across, are called planetesimals, the first real building blocks of planets. The solar system at this point was a chaotic and crowded place, a cosmic construction zone filled with countless planetesimals whizzing around the young Sunday. Collisions were constant and violent. Some were destructive, smashing planetesimals back into dust. But others were constructive, allowing the biggest ones to grow even bigger by sweeping up their smaller neighbors. These winners, now called planetary embryos, were about the size of our moon or Mars. For tens of millions of years, this game of gravitational billiards went on, with a few big winners emerging from the chaos. The entire process of building the rocky planets may have taken up to 100 million years to finish. Out beyond the frost line, accretion was supercharged. With access to all that ice, Jupiter grew incredibly fast, becoming a true giant. Some studies suggest it started forming less than 1 million years after the Sun itself. Its enormous gravity allowed it to pull in not just solids but also huge amounts of hydrogen and helium gas directly from the nebula, ballooning into the gas giant we see today. Jupiter became the gravitational king of the solar system, and its massive pull shaped the orbits of everything around it. Saturn formed soon after, followed by the ice giants, Uranus and Neptune, which took a bit longer since the disk was thinner further out. Back in the inner solar system, the final assembly of the rocky planets was underway, and it was an era of colossal impacts. One of the most important events in our own planet's history was a collision on an unimaginable scale. Around 4.5 billion years ago, a Mars-sized planetary embryo, now nicknamed Theia, slammed into the still-forming Earth. The leading theory, known as the Giant Impact Hypothesis, suggests this cataclysmic event blasted a huge amount of vaporized rock from both bodies into orbit. While some models suggest this debris gradually clumped together, other recent simulations show the Moon might have formed in just a matter of hours, an almost immediate consequence of the smash-up. This theory is the best explanation we have for our Moon's existence and its many strange properties. After about 50 million years of packing on mass, the core of the proto-sun hit a critical tipping point. The temperature and pressure became so unbelievably extreme that nuclear fusion ignited. Hydrogen atoms began fusing into helium, releasing a torrent of energy. Our sun was born, and it burst into light. This moment changed everything. The brand new sun unleashed a powerful stream of charged particles called the solar wind. This wind swept through the solar system like a cosmic broom, blowing away most of the leftover gas and dust from the protoplanetary disk. This brought the main era of planet formation to a close. The gas giants couldn't get any bigger, and the raw material for building new worlds was mostly gone. What was left was a young but recognizable solar system. It was still a messy place, Planetary orbits were shifting, and leftover planetesimals, asteroids, and comets were raining down on the young planets in a period we call the Late Heavy Bombardment. These impacts, while destructive, may have been a vital delivery service, bringing crucial ingredients like water to the inner worlds, including our own. If you're as fascinated by this journey through cosmic history as we are, consider subscribing and ringing the bell to join our community of explorers. There are always new discoveries being made that are changing our understanding of how we all got here. Over hundreds of millions of years, the solar system finally started to settle down. The gravitational dance of the giant planets sculpted the asteroid belt and flung comets out to the system's farthest reaches, forming the Kuiper belt and the Oort cloud. The bombardment faded. The orbits stabilized. From a vast dark cloud of recycled stardust, a star was born, and a family of worlds took shape around it. The story of our solar system is a 4.6 billion-year epic of violence, chaos, and incredible creation. It's a reminder that the iron in our blood, the calcium in our bones, and the carbon in our DNA were all forged in the hearts of stars that died long, long ago. We are, in the most literal sense, made of stardust. And that chaotic ancient history isn't just the story of the planets. It's our own origin story.